friends, I'm very happy to present my greetings at the opening of the new chapters of our series of webinars on science, technology, and innovation. Today, we will explore towards climate neutrality within 2050, Italy-Japan approaches for photovoltaic energy deployment, organized by the Embassy of Italy in Tokyo through our scientific counselor, Professor Enrico Traversa. Thank you, Professor Traversa. Under the push of the new decarbonisation strategy of the Japanese government, and after illustrating the research on hydrogen in the previous webinar, today we will concentrate on solar energy. Solar energy is the fastest growing renewable energy in Japan. In fact, electricity produced in Japan with solar energy passed from 0.3% of the total in 2010 to 7.4% in 2019. The increase in Japan photovoltaic has also been stimulated by Italian efforts. I'm very glad to have Engineer Rimbotti to tell us his success story of implementing Italian know-how in Japan with the installation of a photovoltaic plant in Fukushima. Japan is at the forefront in research and application in photovoltaic. We have the privilege of hosting as speakers Professor Miyazaka, who discovered the new Perovskite materials for highly efficient solar cells, and Dr. Mishima of Kanika Company that hold the world record of efficiency for industrial solar cells. I thank you very much, our distinguished Japanese speakers. For the Italian side, Professor Vomiero and Professor Di Carlo are two of the most creative minds in the photovoltaic arena worldwide, and I am very pleased that they complete the list of our speakers. Aim of this event is to update about the photovoltaic related technology in Italy and Japan, thus exploring the possibility of further collaboration and synergies. I am sure that you will enjoy the webinar. I wish you a very fruitful discussion and a very stimulating learning experience. Thank you very, very much.
So Traversa, floor is yours.
Good morning, everybody in Italy. Good evening, good afternoon for everybody in Japan. As you saw, unfortunately, the ambassador for other engagement could not be, other unforeseen engagement could not be with us, but in any case, he wanted to appreciate your efforts and your presence at the webinar with this video message. So we will have a very interesting program today with 4 speakers, as already mentioned by the ambassadors, plus a sort of special guest for showing the how Italian technology can find the way to success, to commercial success, even in Japan. As housekeeping, I mean, we will have a final discussion with the speakers, and if somebody has a question and answer, questions for the speakers, they could write in the Q&A box, and I will try to accommodate the request as much as possible. So I think we can start with the first talk of from Pier Francesco Rimbotti from Infrastrutture, which he will show us his success story in Japan. Please, Engineer Rimbotti.
Thank you, Professor Traversa. Thank you to the Italian Embassy, and thank you everybody for taking the time to spend with us. I would like to speak about two things. First of all, our company and our experience in Japan, which has been very positive, and I'm very thankful for all the support that I received. I will try and share my screen now, and also put it full mode, if I remember exactly how to do it. Fine. So our company name is Infrastrutture, and we are active investors, sponsors, engineers throughout different parts of the world in the renewable and environmental circular economy sectors. In particular, we have offices and presence in Italy, in Spain, in France, in Japan, and in Latin America, especially in Chile, Colombia, Brazil, and Peru. These are all countries which are very stable, very strong economic and political climate for renewables, and also good investment locations for our projects. As you see, we have important projects both in construction, in operation, and in pipeline, because the moment now to invest in renewables is extremely important, especially after what we saw from COVID. We saw a great acceleration of both government and private entities to switch to renewables. Overall, in the world, we have about 8 offices, and we're 80 senior managers and experienced professionals. And we have already brought to market more than 500 megawatts, and now we're working on 2.5 megawatts across the different parts of the value chain. So Infrastrutture has asset companies, an engineering company, O&M company, development effort, of course, joint ventures. And we have also some strategic technology partnership, in particular with TVB Solar, which is a breakthrough thermal panel. I've been in the power business since a long time, and this is a new technology. Over 160 patents, and can produce hot steam at 180 degrees from solar. So as you will understand, is extremely new product, and it's right now reaching the market from the first manufacturing units. We have another strategic partnership with NextWave. We will speak a little bit about it. It's a disruptive wafer manufacturing technology, and which is a spin-off of Fraunhofer, and allows increase of efficiency and a substantial decrease in cost of manufacturing of wafers. We also have another partnership with one of the largest internet incubator, because also from this field we expect a lot of changes in the energy world. So we operate, we have worked on a specialized IT ERP system for the company, which allows people to work worldwide on a real-time basis and share documents and decisions and processes. As you are all aware, making a renewable energy project takes years and years of development, of careful communication, education across different parts of society, going from the local public to the administration, the government, the region, the authorities for agriculture, fire, water, and everything. So it's a very complex, interrelated communication which needs to go on very professionally. And I think that this helped us a lot in doing the projects that we did in Japan and to help make the communication, which is typically one of the hurdles that companies need to confront when they come in this wonderful world called Japan, which is very sophisticated, but not necessarily very easy for foreign companies to come in. Of course, we have all the necessary certifications, and that's another part of our company culture, which is very important. We were the first company in Italy to attain health and safety certification for our solar panels, so that we were the first in Italy to attain that. So that really highlights how we want to be investors in this field. So we started, we were looking at Japan as a potential market to work with, and of course with a lot of fascination. Japan is the third economy worldwide and potentially the most sophisticated. But at the same time, in energy, it is a very fragile country because it has very, very little autonomous in-house production of oil, gas. So we were there, and we decided after the great earthquake in Fukushima, we decided that we should play a role and that we should put our experience to the benefit of the country. Also because I firmly believe that the synergy between the two cultures is extremely important. So we were, I think, the first company, non-Japanese company, to win a public tender in Japan. We actually won 2 public tenders in Japan. And we really thank the administrations that made it possible, that believed in our company, in our know-how. We are now working on, we are about to announce the financing from a Japanese bank of a solar project in Japan, which is another very good success for us, and a very good success for cooperation between the two countries. And we are now working on a number of other projects in different parts of Japan. In particular, we had a very interesting project in Kumagaya, where we implemented over about 10 hectares a solar plant on in a basin which can be inundated by water when there is a potential for river overflow. So the engineering of this project was done very, very carefully, and it really involved, as you may imagine, a huge amount of different authorities, all justly preoccupied by the potential impact of making mistakes in the engineering. This plant was inaugurated several years ago now, a couple of years ago, and it's working properly. And I think the relationship with the municipality is very strong with our people in Japan. So again, in this, we faced many challenges. First, that there had been another project which was built to other engineering criteria, but we felt that these engineering criteria were very important, and as a whole, we all finally decided that this could be done. This is just a number of different other projects that we've done in Japan, and we look forward to doing more. if I can now show you a little bit about, you have to allow me a second to change presentation. I want to speak to you about next wave, which is, sorry, gentlemen and ladies. Okay, I hope I can do it. So we invested in NextWave a few years ago, and is a really disruptive technology in producing wafers for the solar industry. So this little bit here, and fundamentally, it has a very, very different deposition type of process in order to produce this wafer, and the thinness of the wafer can be reduced to, actually our target is 30 micrometers. So obviously there is much less waste. So the process allows to go from chlorosilane and polysilicon directly to the wafer with one single manufacturing process. So from chlorosilane, we go to Epinex, the wafer with only one process instead of crushing, ingot pulling, cropping, bricking, and sawing, which is obviously reduces the capex of the manufacturing by around 50%, 90% waste reduction, 50% less energy, and a very high quality wafer. The wafer that we can produce is full square, and especially it is extremely homogeneous across the band of the square. There is no Somax, and therefore we think that this process, which is right now in pre-industrial, so the demonstration units are running, and it's pre-industrial, will be very useful to provide further advantage to the solar market. I know time is limited, so I thank you very much for your attention and remain available for any further questions later on.
Thank you very much for this very interesting talk, and very nice to see how you were able to overcome the Japanese stakes for foreigners in business. And so after this very interesting introduction, we are passing through the other talks, I mean, more scientific, let's say, even if some scientific contents was also given in this, in the first presentation. And so I leave the floor to Professor Miyazaka from Toin University of Yokohama. And Professor Miyazaka is very well famous for having discovered new perovskite materials for solar cells, and we are eager to listen to his talk. Please, Tom.
Thank you for introduction. I'm Tom Miyazaka from Tokyo, Japan. Let me share my slide with all of you. Just a moment. So can you see?
Yes.
Perfect. Okay, thank you. So good morning, ladies and gentlemen in Italy, and good afternoon, listener in Japan. My talk would focus on the perovskite solar cell, now one of the champion solar cell in terms of high efficiency. And what about the research activity in academia and industry? So, it's my pointer. Okay. First, let me introduce my university, Toin, Yokohama. This is about several kilometers, maybe 20 kilometers the west of Tokyo City, in suburb of Yokohama. So the commercial solar cell, champion solar cell is still a silicon crystalline solar cell. In terms of the highest efficiency, 26.1%, and cost may be the cheapest in the photovoltaic module. And the competitor is the CIGS and the cadmium telluride, but cadmium is not allowed to produce in Japan, this country. So this solar cell have achieved the conversion efficiency beyond 20%, but organic type solar cell, this is advantageous in terms of solution processable. So we can code solution to make a very similar solar cell on the substrate. The typical one of organic thin film solar cell and dye sensor solar cell. This is a chemistry-based solar cell. But so unfortunately, this solar cell efficiency was much behind those of commercialized solar cell and less than 20% or more or less 50%. But exception was the perovskite solar cell, which achieved now 25.5%, almost comparable with silicon solar cell. So when you see the so-called spectral sensitivity of perovskite solar cell, its shape is similar to gallium arsenide. It is a champion semiconductor achieving the highest efficiency with a single semiconductor, 28-30%. But perovskite is almost excellent semiconductor having a very strong absorption, which takes place 800 nanometer. The gallium arsenide can absorb the light up to 900 nanometer. The gap is 100 nanometer, but both cells is able to harvest all visible light. Silicon can respond up to the infrared region, but the light absorption power is much less than this perovskite and gallium arsenide. When we see the recent progress in the efficiency of perovskite solar cell, it's plotted in yellow plot. That we now compare this one with silicon. Silicon is still its efficiency is increasing slowly, but perovskite, this development started to 2012 and rapidly increased the efficiency now. So we can see how quick this progress took place. So we first discovered this halide perovskite semiconductor for use in photovoltaic application in 2005 or 2006. Efficiency was still low, 2%. And then 2009, we published the first peer-reviewed paper reporting perovskite photovoltaic cell able to exhibit 3.8% still low efficiency. But what happened is in next 3 years, 2012, the efficiency was boosted up to beyond 10%. So all engineers working on the photovoltaic cell change their mind. Well, what is the strange materials able to achieve 10% efficiency by solution process? Anyway, we published this result in Science. That this is the evolvement of perovskite solar cell. So the name of perovskite comes from the Russian mineralogist Perovskite living in 19th century. But the first discovery of perovskite was oxide perovskite, typically calcium titanate. But before the turn of the century, 20th century, Wells, German researcher, found the halide perovskite. This is a replacement of oxide to halide. So that time, the first material was cesium lead halide. So, but no one tried to apply this one for photovoltaic application. But so recent 10 years, perovskite is more famous for use in LED or say ceramic, and it's a very popular material for high efficiency solar cell. But interestingly, halide perovskite have been commercial ABX3. This is ionic conductor, very strong ionic materials. So A side, B side is a cation, X side is halide. So it can be soluble in polar solvent like water, a small amount. So we can dissolve the materials and coat on substrate, and just drying up the layer, we can deposit the crystalline of perovskite. So here you can see black perovskite and yellow one. This is made by just changing the element of halide from iodide to bromide. So we can easily change the color and band gap of the semiconductor. One excellent performance is light absorption power. This power is 10 to 100 factor larger than the crystalline silicon. This is a crystalline silicon curve and perovskite here. So very thin layer of perovskite can absorb sunlight. What is thickness? It is less than 1 micron. Almost, also the wavelength responsivity is tunable by just changing halide element, the ratio of bromide and iodide. So we can make all colorful the variation of perovskite semiconductor. We published the first result in 2009, depositing perovskite crystals on TiO2 semiconductor to sensitize TiO2 by using perovskite light visible light absorber. We found the change in the spectral sensitivity between bromide and iodide. It's the first paper. Fortunately, the perovskite crystals can sensitize TiO2 by injecting the photo-excited electron to TiO2, causing a so-called photocurrent. Band gap was typically 1.5 to 1.6. This indicates all visible light is efficiently absorbed by single layer of perovskite. So the thickness is also very, very thin. Here's a sectional view of perovskite solar cell. Perovskite layer sandwiched between the whole transport layer, electron transport layer. Absorber perovskite thickness is much less than 1 micron. So this is a typical thin film solar cell, like a gallium arsenide. So based on this structure, we can make a very lightweight, flexible, thin film solar cell. So perovskite layer can work with thickness of around 0.5. Sorry, this is a mistake. 0.5 micron meter. So this is an example of a device we are making in our laboratory. The whole transporter is also the organic or inorganic hybrid. This is spiral metal commercial available one. So we are making a very small cell to test the photovoltaic performance and also this stability. Shape is almost 2 to 1 inch square large, having 3 independent solar cell coated on glass or plastic cell. So what is the advantage? Sphericity is output voltage from solar cell is relatively large. This has been enabling high efficiency of solar cell. Light absorption is very intense, and we can change the band gap. So band gap is tunable, and cost is very, very low. Can you imagine the perovskite film costs just $1 to $2 per square meter? That's the material cost. The all layers printable, low temperature processes are applied, but future challenge is how we can stabilize the cell to ensure stability to 200 degrees. Now we are making all inorganic composition without using the organic element in the composition. So this is the efficiency, power computation efficiency is exhibited by this equation. So the power output is a product of ampere and current and voltage. So incident light is typically 1,000 watt per square meter. So if the solar cell has a power conversion efficiency of 50%, we can imagine 150 watt can be obtained from 1 square meter module. The challenge is how we can increase current output and voltage output. Fortunately, perovskite has a very unique nature, so-called defect tolerance, only having very shallow traps. So this leads to high efficiency of photoluminescence and PV performance. This very shallow trap is enables suppressed recombination of light excited carriers. So this is enabling very, very high output voltage from solar cell. This video shows now the perovskite source is coated on the substrate, and this spin coated machine is making a thin layer of liquid. Simultaneously, the solvent is evaporated in almost within 1 minute. So you can see it's a very brilliant green emission from this crystalline. That indicates the crystalline layer was formed on the substrate in very, very short time. So this was now exposed to UV light to excite perovskite, and they was coated in the alumina insulator. So if we replace this substrate to say conductive electrode, all this energy is converted to photocurrent. So this very intense emission indicate how the photoexcited carrier are stable on the perovskite. So this kind of this outline we summarized in our recent paper in chemical review. So if you're interested, all information is included in this record. So other thing merit is power generated per unit weight is the largest among all PV devices, because the photovoltaic layers can be made very, very thin. But we can also, as a chemist, synthesize by changing cation anion, replacing the organic cation with inorganic cesium like this. So this is a typical, the so-called multi-cation lead halide perovskite coated on TiO2. You can see it very large grain of crystalline is coated on TiO2 basement. And I think it's a very beautiful structure of the layer structure of perovskite. So we have been making effort to make smooth and large grain based perovskite layer to enhance the efficiency. Also, to cost reduction, we hope to create the ambient air process without using vacuum, without using a dry room. So we could achieve efficiency beyond 20% of these materials. And recently, we tried to dope germanium to lead to improve the quality of crystalline. So this is one of our champion efficiency of single cell, 22.5%, and with an output of voltage, almost 2 voltage. But next stage is to make the all inorganic perovskite. In other words, the organic element-free perovskite to ensure high thermal stability, hopefully up to beyond the 200 degrees Celsius. So our choice was cesium lead halide, this composition, and cesium replaced the organic methyl ammonium or holmium cation. So as a partner of the whole transport materials, this is also solution processable. We chose the polymer, copolymer materials as a whole transport materials. This is also has a relatively high thermal stability. By making this solar cell, by coating perovskite on the cheap tin oxide layer, we could achieve 1.4 voltage output. This is very recent result we published last year. So this is very impressive performance of perovskite in terms of very, very high output voltage released from perovskite solar cell, 1.4. Band gap of this cell was 1.9. So there was still loss of 1.5 volt. But I think this 1.4 or 1.42 volt is the highest voltage obtainable from single perovskite solar cell. So thanks to the friendship between Italy and Japanese laboratories, we are doing a long-term running collaboration with the Italian research team. This is Alessandro Albati working in senior IM in Catania, Sicily. We have started this collaboration from 2014. So thanks to your effort, the administrative research based on the high resolution term was very helpful to analyze the mechanism of solar cell performance. So what about industrial application? One is making super lightweight and flexible perovskite solar cell having a very high energy density. So you can imagine this kind of application, especially the promising application is there in IoT industry, indoor and mobile application. We also fabricated such kind of flexible solar cell coated by perovskite from solution, and total thickness of device was 125 micron, very, very thin. Still, the cost of perovskite material is $1 or $2 per square meter. This is the cost just perovskite without the substrate and other, say, materials. So this is a, I don't have much time to introduce. Anyway, the coating process is mostly by the solution process or by using inkjet. So the very thin film is has very high durability against bending, mechanical bending up to 1,000 bending cycles. The future, the single cell efficiency can be reaching close to the 25% efficiency by further enhancing the output photovoltaic. Exactly the open circuit voltage. The shock requires a limit, so-called shock requires a limit is 1.32. So if we could achieve this level, still the perovskite solar cell, the efficiency can evolve up to 27%. And also in future, my dream is to mimic the level of gallium arsenide, 28%. The outlook of application is huge. It's not limited to solar cell, but image sensors, X-ray detectors, and visible light detectors, light emitting diode. And okay, this is a rooftop application, and the window application almost attractive. The solar cell can utilize the light from both sides of the device. Other application, the IoT. In Japan, the Enrico company commercialized this one for using computer. This was attached to the dye sensor solar cell solid state. But without replacing this one with higher efficiency perovskite solar cell. If we could replace this on perovskite, the power output and the indoor light, like 200 lux, very weak light, can reach 22 microwatt. This is much, much higher than those power produced by silicon indoor illumination, because silicon, silicon cannot utilize infrared. Perovskite is focused on the use of visible light. It's from indoor illumination. The layer also can be made by inkjet printing method, and recently we are applying and measuring the durability of perovskite for use in space environment with collaboration with JAXA in Japan. They want space solar cell required for space satellite, having thin film light and lightweight, flexible, and low cost. Now, the private company almost launching a small rocket, so they are not accepting very expensive solar cell. So low cost is also important. The issue is to ensure high durability against the irradiation in space, like electron, proton. And we finished some previous test to show very high proton irradiation durability, tolerance of perovskite. It's a kind of unexpected result. Perovskite flower cell having damage of the irradiation still active in producing power before, after the irradiation. Before one is blue, after one is red. So thank you. I just scanned my list outline work. We are doing international collaboration in Italy, China, Germany, Russia, and doing a project JAXA and also NATO. Thank you very much.
Thank you very much, Professor Miyazaka. Very interesting talk. I forgot to mention before your talk while presenting you that the reason why we invited you is just because you had the collaboration with Italy. And so that's what your presence was particularly important for us for also as testifying a good example of collaboration between Italy and Japan. So now we can move to the second talk, and Professor Alberto Vomiero from Ca' Foscari University of Venice. And so Alberto, the floor is yours.
Thank you very much, Enrico, for your kind invitation and introduction, and for giving me the possibility to illustrate the results of my research on luminescent solar concentrators. I hope the screen is visible now. And
yes.
Then let me go ahead. Thank you. Today I would like to talk about luminescent solar concentrators. What's new for building integrated photovoltaics? Luminescent solar concentrators are not a new technology. It dates back beginning of the 70s of last century, but it was quite promising at the beginning. Then it was abandoned because of a few issues I will discuss today. But there has been a renaissance of this kind of technology, mainly related to application of suitably tailored nanomaterials. And my research has developed in Italy, Sweden, and with a few collaborations in Canada and China. And the point is that application of nanostructured materials, and specifically today, I would talk about semiconducting quantum dots and carbon dots, are key to boost the performance of this kind of technology. So in our lab, we are trying to research a few topics related on nanomaterials for energy and environmental applications. And I will focus today on how the charge dynamics can affect the optical properties of nanocrystals, which can be integrated in luminescent solar concentrators. Why luminescent solar concentrators? Well, building integrated photovoltaics includes a series of technologies which can be applied for self-powering of the buildings, and it has been relaunched at the EU level within 2050 perspective. And here you can see a few examples of building integrated photovoltaics which put together different features. The first one is the very famous facade fabricated by Dyson-style solar cells at 12, but then with the time several features have been requested by architects. One is the color. As you can see, you can obtain colored facades. Another one is efficiency. You can see building integrated photovoltaics built up from silicon solar cells. Other features which can be of interest are the transparency or semi-transparency of windows. So you can have transparent photovoltaic windows or non-planar surfaces. And of course, in this case, the efficiency is limited compared to fully absorbing layer, and so the photo conversion is lower, but of course you can use it as a window. So different kinds of applications call for different materials which can be applied for the purpose. And luminescent solar concentrators is one of the possible technologies in this field. Is building integrated photovoltaics an interesting feature? Well, I'm reporting here news from the Courier a few days ago, which they say the global BIPV market size is projected to reach USD 3.96 billion by 2028. Which is a significant increase, expanding at CAGR 26% in the forecast period 2021-2028. And of course, it includes a series of technologies, and I will focus just in one for today. What are luminescent solar concentrators? Luminescent solar concentrators are essentially colored, transparent, or semi-transparent windows in which the light is absorbed by dye molecules or nanocrystals within a transparent matrix. The slab is acting as a waveguide, so part of the light is re-emitted by these particles, can be waveguided at the boundary of the slab and can be photoconverted by typically a thin and small silicon solar cell. Part of the non-absorbed light is transmitted, and from this you get the semi-transparency of your layer. This is an old idea, as I was mentioning. So what's new? The issues related to luminescent solar concentrators rely with the dye photo degradation at the beginning of the history of this technology, of the strong reabsorption losses and the strong scattering. Reabsorption occurs because part of light which is emitted by the nanocrystals can be reabsorbed by the other nanocrystals or dyes, while the strong scattering is mainly generated by the matrix. The scattering issue can be avoided by using the PMMA matrix, while one of the best ways to remove the strong reabsorption losses is to increase the Stokes shift of our materials. So as you can see here, it's reported at two different levels of Stokes shift. And of course, when the Stokes shift is high, you have strong reabsorption of your light. This is reported for dye molecules, but the good point here is that with by tuning nanocrystals, you can really tune the Stokes shift and obtain the results you need. In a couple of papers, my group and Jean Roncalli is probably the most competent person in the world about luminescent solar concentrator, relaunched this technology. We were a bit more optimistic than Jean. He was a bit pessimistic because the technology had still some issues, but it has been put under focus in the last couple of years. I will describe now the latest developments by using semiconducting nanocrystals. Semiconducting nanocrystals allow you to change the energy gap of your crystals, so the absorption and the emission, just by tuning the size, and that's the first step. But then you can tune the electronic properties of these materials by playing with their complex structure in a core shell geometry. They have been proposed for photovoltaics applications also in solar cells due to intraband transitions and multiple exciton generation there. But here we're not interested into these features, but rather we are interested in two main features for these crystals: the high quantum yield, so the possibility to re-emit as much as possible of the absorbed radiation, and the large Stokes shift. Of course, the Stokes shift relies with the loss of energy, but the energy lost in this case is almost negligible. So we focused not only on visible quantum dots, but also on quantum dots of lead sulfide, which are active in the near infrared region. And one of the issues, unfortunately, for these quantum dots is that they are strongly affected by surface oxidation. As you see here, by changing the size, of course, you can change the absorption and the emission, so the color of these crystals, and you see you can easily prepare quantum dots which are not affecting the transparency in the visible window for your materials. And to avoid the surface oxidation, we tried to cover our crystals with an insulating shell. It's a cadmium sulfide shell, and we succeeded in demonstrating that the core shell is much more stable than the simple crystal. We also tried to investigate how the core shell structure influences the charge dynamics when you have your quantum dots integrated in a few different matrices. We first tried with the titanium oxide and tin oxide by demonstrating that by changing the size of the core and the thickness of the shell, you can tune the ability of electrons to be transferred from the photoexcited crystal to the oxide. And of course, this is killing the photoluminescence of your system. So you want to be able to avoid this kind of processes, vice versa in the solar cells. So in the solar cell, you want electrons to be transmitted. In this case, you want not the electrons to be transmitted and to go with radiative emission. And by applying photoluminescence lifetime measurements, in dark you see the crystals which are absorbed in silica spheres, so in a material which is not transferring electrons. You see that by increasing the size of your crystal, you increase the lifetime of the photoluminescence, reaching the threshold of 4.8 nanometers. The same results for silica, saying that at that point, your nanocrystal is no more injecting electrons into the titanium oxide. And the same by tuning the shell. The shell is essentially a tunneling barrier. So the thicker the shell, the highest is the barrier, well, the width of the barrier. And you see that you are able to decrease the injection by tuning the shell thickness. But then by reasoning about the shell thickness, Klimov group proposed a new strategy to broaden the optical properties of these materials. So by proposing a very thick shell, which is covering a very small quantum confined core. And this kind of structure is called giant core shell quantum dots, and it's characterized by classical emission from the shell and quantum confined emission from the core. And tuning the optical properties of these crystals is extremely fascinating. We tried to fabricate giant core shell structures active in the infrared region, so lead sulfide, cadmium sulfide quantum dots. Here the issue is to understand the structure of these materials, and it was pretty challenging to identify the presence of lead sulfide. But then coming to the optical properties, you can see that these crystals present a double emission. When we excite at 430, we have an emission around 500, 490, which comes from the near band edge emission of the classical cadmium sulfide shell, and the emission around 700 nanometers, which comes from the lead sulfide core, which is confirmed by the lifetime of these two emissions, which is in the microsecond range for lead sulfide core, and it's a tenth of nanoseconds for a cadmium sulfide shell. Then by applying ultra-fast pump probe spectroscopy at Polytechnic of Milano, so I'm not an expert in this, but the outcome of these measurements is that we were able to draft an electronic structure for our materials in which the lead sulfide is surrounded by a thin zinc blende shell of cadmium sulfide, which is acting as a blockade layer for holes which are produced in the external shell to recombine into the core and originating the double emission. We were then able to detect also lead sulfide, but then our hypothesis is we can have double emission when we have a very neat interface between the core and the shell. What about if we are able to produce a graded interface? In this case, we are removing the effect of a blow of a hole blockade, and we should obtain a single emission in the close to infrared region. And this is what we obtained here. You see in the right panel, second one, the blue and pink photoluminescence. You see in the double emission for sharp interface, and for graded interface, you see a single emission in the near infrared, close to 680 nanometers emission, testifying that you are really able to tune the optical properties of these materials. And then we also tried to apply Kelvin probe microscopy to investigate the variation of the electronic structure of these materials as a function of the size and of the composition. And here are the topography and Kelvin probe measurements. And as you can see here, let me put attention only on the first left panel. You see that different compositions for cadmium sulfide, lead sulfide, and the composite system are consistent with the decrease of contact potential difference with the size. And then we come to application of these materials. Let me skip this slide for luminescent solar concentrators. So the first point is to recognize that by tuning the shell thickness and the core, you are able to tune the Stokes shift, as you can see here. And the Stokes shift can be tuned because you are able to tune the electronic structure of your nanocrystal. And then once done this, we integrate into solar concentrators based on polymethyl methacrylate. And in the left panel, you see a non-core shell system, and on the right side, a core shell system photoluminescence of spectra taken at a different position, so different distance from the light source to the light detector. And you see that in the case of a core shell, we are able to remove completely the self-absorption processes and to obtain the same shape of photoluminescence irrespective of the distance. So it means that your light is transmitted without being affected. And then we arranged different structures for luminescent solar concentrators in which either polymer or the sandwich glass can act as a light transporter for the purpose. And let me give a couple of examples before concluding. One is about the possibility to use silicon nanocrystals, which are emitting in the close to near infrared region, linked with absorbance in the UV region, so you can obtain transparent or semi-transparent luminescent concentrators, which are also using the UV radiation. So you can broaden the range of radiation which can be used. And then the latest one is about the possibility of using carbon dots with a new method developed by Professor Rogak using a vacuum system. There is the possibility to obtain carbon dots with quantum yield larger than 60%. We integrated into luminescent solar concentrators, demonstrating that the Stokes shift is 0.53 electron volts, so it's pretty large, and we obtained a very high efficiency, optical efficiency of the materials into a device. Efficiency for these devices is indeed an issue because it's critically dependent on their size, and there is no standard at international level. So the community is trying to solve this issue and challenge to define standards for the measurement of the efficiency. And that's it. A couple of slides to say that the research in Italy on luminescent solar concentrators is carried out by large companies like Eni, or small startup companies like Glass to Power, which is an initiative from Milano Bicocca. So before ending, let me acknowledge all my collaborators and colleagues for this project from Venice and Luleå, and thank you very much for your kind attention.
Thank you very much, Alberto, for this very interesting talk and topic with a different perspective. So now we can move to the next talk, which is by Dr. Ryota Mishima from Kaneka Corporation. Dr. Mishima, the floor is yours.
Can you hear me?
Yes.
Yeah, good. So before the webinar, so I faced internet problems. So just a minute.
Luckily, they are solved.
And can you see my slide?
Yes.
Okay. Yeah. Okay. Thank you for giving us a chance to have a talk. I'm Ryota Mishima, working for Kaneka and Kaneka Belgium. So today's title is high efficiency heterojunction crystalline silicon solar cell and its application to perovskite heterojunction crystalline silicon tandem solar cells. It's a bit long. So Kaneka is a Japanese chemical company. So our company has a lot of products such as chemical, plastic film, raw food material for bread, so for eating. So medical devices such as catheter and supplement and so on. Actually, our business field is very wide, and one of them is solar panels. Okay, as an introduction, I'm going to talk about current market of solar technology. So this graph shows the current and future trend of the market share of the solar cell technology, so which is published by ITRPB. So more than 10 years ago, the main player was back surface field, so called BSF cells. But now, so PARC cell have a lot of share. PARC cell has a device structure with near participation against BSF cells. So with this participation, so the performance efficiency can be improved into over 22% in keeping low production cost. And it is predicted that this trend will be expanded in these 10 years. And high efficiency technology, such as heterojunction back contact tandem cell, will be expected to increase the share also. Anyway, almost all of the products on current and future market will be based on crystalline silicon technology. So it's very simple reason. The price of base materials, crystalline silicon substrate is very cheap. and it's still getting lower. Based on this, so our strategy is also simple. So we want to use crystalline silicon technology and so target high efficiency to make a differential point with PARC cell. So next, I will show you the history of our PV activity. Around 40 years ago, so in 1980, we started our activity on thin film technology, so based on amorphous silicon, and we could success commercial production of amorphous silicon solar cell. And then, so we became the first company to manufacture the tandem solar cell with the stack of amorphous silicon and microcrystalline silicon. In 2000, as I mentioned, so the price of crystalline silicon has been going down so significantly. So we had to change our strategy from thin film to crystalline silicon solar cell. At that time, so we established the European lab at IMEC in Belgium. Today, I'm joining this webinar from Japan due to business reason, but normally I'm working so here. And since then, we have been focusing on heterojunction solar cell, heterojunction solar cell, and we could realize so some record efficiency on this technology, but we still continue to make an effort to innovate the technology with this research and development. So what is the heterojunction cell? So in heterojunction solar cell, amorphous silicon is coated on the surface of crystalline silicon so to make it passivated, and it leads to high VOC and fill factor, so with smaller temperature coefficient. As mentioned, amorphous silicon is our core technology, and we had a long experience, so it was easy to jump into this field. And the other aspect, so heterojunction solar cell can realize a fast process with a low thermal budget. The temperature is less than 200 degrees. And heterojunction solar cells are divided into two types by electrode design. One is so we call top rear contact. So crystalline silicon is sandwiched by amorphous silicon and TCO, transparent conductive oxide. Then, so its top and rear contact is literally so metal grid. Electrode is put at both sides on TCO. At the beginning, we started to develop this type of heterojunction technology and could achieve the record efficiency of 25.1% in 2015. And the other one is back contact, where both polarity electrodes are integrated only at the back side. So this is also passivated by amorphous silicon, and so actually the passivation quality was a key issue to improve the efficiency. Of course, it has no electrodes at the front side, and there's nothing to the shading. So high current can be obtained, and so normally in the case of top and rear contact, so there's a trade-off between electrode resistivity and shading loss. But so back contact can design the electrodes more freely. So since we don't need to take care of such kind of shading at the front side. Anyway, so we did optimization, everything. Then we could become the first institute to reach the efficiency of over 26%, so JSC for over 42 milliampere, VOC over 740 millivolt, the fill factor is 83. That is so very good. This result was published on Nature Energy. And finally, we reached the efficiency of 26.7%. So this is noted as a record efficiency of crystalline solar cell in the efficiency table like this. Maybe you may think that this update of efficiency from 26.1% to 26.7% is not big. But based on our result, we estimated the practical limit of efficiency, and it was 27.1%. So since we are almost close to the limit, so it was very difficult to get a small update. And we made the module also with the heterojunction back contact cells. That efficiency was 24.4% with the area of 1.32 square meter. This is also record module efficiency on crystalline silicon technology. So it is noted on the efficiency table. This also like this. And you can find another record efficiency of 25.1% on gallium arsenide based module, which is more expensive technology. Actually, our technology is getting close to them. So next, let's move on to our business part. The standard products are for residential housing. But as I mentioned at the beginning, the share of park cells is not quite big in this market. We have to find a new application which is suitable for our PV. So now one of the targets we are thinking is building. So we hope we can provide customers with a total solution of PV for building through our technology we have developed so far. For example, the rooftop, in some case, top and rear contact heterojunction solar cell with bifaciality is helpful to get more light with the deflection from the ground like this. And thin film technology, thin film PVC see-through. So PV is helpful for the replacement of window and transparent balcony. And of course, our back contact module can be used to achieve more energy and uniform color according to the customer's requirement. And another example, we developed the exterior system, so-called multi-solar system, in which electric power is generated from the window and the wall on the building. So we know it's strictly required from building company and designer to meet aesthetic design, so heat installation and light management. For all window, see-through PV is applicable. I guess people imagine semi-transparent solar cells as see-through PV. But this kind of semi-transparent PV has some kind of color. So sunlight is irradiated into buildings through color filter and with PV. But but we know people prefer natural sunlight. It is more important to keep people inside the building comfortable. So on our see-through PV, we developed some threads. Natural sunlight can irradiate into the building, and another part can generate energy. Actually, this type of see-through PV is applied to the New Japan National Stadium like this. In addition, in the multi-solar system, for wall and the facade area, our back contact can be applied to keep it black. The advantage of a back contact cell is not only high efficiency, but also aesthetic design. So it is realized by the uniform and black color due to no electrode on the front side. So this is the roof tile So this is the roof-tile module with back contact solar cell for residential housing. By putting this module on the residential housing, so black roof, so completely black roof can be realized. It is designed to make it easy to attach the roof of residential housing. It's a kind of replacement of slate. And this is the facade type of module for BIPV. So it looks like just black panel. And in near future, so we expect that automobile also has solar panel on the roof. So recently, our PV module was applied to Japanese car companies, so Toyota's low-speed automatic driving EV, so called e-Palette. And to realize the integration of our solar module with commercial car, we developed the technology to fabricate 3D curved, not only one dimension, so 3D curved PV module also. Actually, so this picture shows our prototype of 3D curved PV module. Okay, so finally, I'm going to explain about future. So we still continue to continue the development of high efficiency solar cell, but it's difficult to increase the efficiency with only crystalline silicon solar cell. So as I mentioned, since the practical limit is 27.1%, so we are almost there. So we need to think about multi-junction solar cell. And considering current and future market, we think there's no doubt to use crystalline silicon due to very low price. So normally, crystalline silicon can absorb the light, so infrared wavelengths. So we should find a partner which is good at absorbing the light, low wavelength light to this region. So perovskite solar cell is one of the most promising partner with crystalline silicon solar cell. So perovskite solar cell is invented by Professor Miyasaka. And normally it's made on glass TCO substrate, but it's known that tandem solar cell can be made in coating perovskite solar cell on crystalline silicon solar cell. Like this, but it's still under research. We need to find the best configuration for how to stack these two types of solar cell. So one point is band gap of perovskite. The band gap of normal perovskite is 1.55 EB to 1.6 EB. And now the best case of the tandem cell is 1.68 EB. So the Germany group achieved 29%. And but it's connected in series called two terminal. But some calculations say that much wider band gap is suitable for tandem cell. We need to continue the challenge to make the perovskite materials, which is suitable for crystalline silicon solar cell. On the other hand, it's better when we think about 3-terminal or 4-terminal. So we don't need to take care of the band gap. So according to this calculation, efficiency is almost the same, independent of band gap. So in near future, we will try to tackle this kind of problem. So Kaneka is a chemical company, so we get used to chemical engineering, so like band gap tuning or finding new transport materials. And as I mentioned, so we are the first tandem manufacturing company of amorphous silicon and microcrystalline silicon. So we know how to stack this kind of technology. And so as we mentioned, so we have some record efficiency on both heterojunction solar cell, not only two terminal and but also back contact solar cell for 3 terminal. So we want to continue so this kind of experiment, and so we will try to achieve much higher solar cell. So this is a summary. So we achieved the efficiency of 25% on top bottom contact heterojunction solar cell, and the world record efficiency on of 26.7% was also achieved on back contact structure, and the record module efficiency is 24.5%. And so we will try to get over 30% on perovskite heterojunction tandem structure. So this is our future plan. Thank you very much.
Thank you very much, Dr. Mishima. It's very interesting how the progress were made for this type of fuel cells. So now we can conclude the scientific talks with Aldo Di Carlo, Professor Aldo Di Carlo. Aldo is the director of the CHOS laboratory at the University of Rome Tor Vergata. And recently he became also director of the Institute for Structure of the Matter of the National Research Council of Italy. So please, Aldo, the floor is yours.
Enrico, thanks a lot. It's really a pleasure to be here today, and I will discuss about the activity we are doing down in Rome, both at the CHOS, the University of Rome Tor Vergata, and at the CNR. They are very close to each other, so it's easy to work together. So I will, we are in Rome. Unfortunately, our laboratory is 10 kilometers from the center of Rome. So we are in the countryside, which is quite good because we have enough space to develop even semi-automated deposition system and join the bridge, join the basic research and more applicative research like high TRL research. So I will discuss about the printing technology for photovoltaics. Of course, this is not limited to photovoltaics. It's also quite extensively used in other printed electronics. So the main idea is to go from conventional electronics, where you need high temperature doping, vacuum gases, control environment, to a more solution process where you can use printing methods like inkjet, gravure printing, slot die, and so on, to create your final system or device. So this is very suited for the Italian system of company, which are very small. So it's a very suited for small, medium enterprises. So for this reason, is a model, is a business model, also technology-driven business model, which is very suited for the Italian infrastructure of company. So let me just first present to sketch. The first one is from dye solar cell for building integration. Dye solar cell is a biomimetic cell. So this is the sketch of the solar cell. This is a titania sponge where a molecule is attached on, and then there is an electrolyte. Photon is captured by the molecule. Electron will move in the titania, and all, let's say, will go back through the electrolyte to the counter electron. So this is a very simple system invented by Michael Gretzel at the end of the 80s. And it's very interesting because you can control molecule, you can control transparency. And for example, you see is a plethora of colors. And if you make a plot, the plot, let me show you the options. Sorry, this one. Okay, so you see a transparency and efficiency plot, then you can put changing the thickness of the titania, the colors, the molecules, and so on. You can make this kind of plot that relate transparency and efficiency, which is quite good. I mean, you can get 5% with 40–50% of transparency for this kind of solar cell. So we were asked to develop a pilot line for to industrialize this process, and this is what we have done. We have done together with a company, Permestelisa, that nowadays I believe is Lixil, is a Japanese company. So this is a quite interesting bridge between Italy and Japan. And we realized a pilot line. You see the size of the module is A4, is a semi-automated, almost automated system where you can create disolar cell with all the process up to the final laminated panel. This is the kind of module you can do, change color, and also in the bottom left is the panel, the disolar cell panel. Everything is assembled by a robot, so it's really automated production line. And this is what we can get, is a kind of average on the module is 5.5% of efficiency, and the transparency of this module is 30%. The main effort we did is to stabilize the technology, because at the very end you need to bring this to the market. And then we were made efforts, I believe 5 years effort to stabilize the technology. And then you see the main IEC 61646 test, like UV preconditioning, humidity freeze test, and damp heat test. And then you can see all this can be passed with a variation of efficiency of less than 5%. So a relative variation. So you can see that this kind of technology is quite rugged. And we had a nice collaboration this with Japan, with the Professor Hironoki Arakawa from Tokyo University. So, but as we have seen from the Miyasaka-san talk, there was a breakthrough in the field that came from disolar cell. This is very important. So Miyasaka and his team were the incredible idea to replace molecule with halide perovskite, and this was the starting of the new field of halide perovskite. So a few percent, as Miyasaka-san said, in 2009. Then there was a transfer from liquid to solid state, let's say still disolar cell. At the very beginning, people were considering this was just an evolution of disolar cell, but then later on, it was realized that this was a completely new technology that was quite separated by disolar cell. Okay, so this is just a sketch of the mesoscopic version of the disolar cell. This is a 10 image we did some time ago. And then you can see there is a mesoporous region. There is the perovskite is also in the mesoporous region of titania. Then there is an overlay, and then electron and hole transporting layer. So as you can see, there are a lot of interfaces. So, and as Emilio Palomares said some time ago, efficiency and stability are really controlled by the interface, which is quite conventional for any electronic and optoelectronic device nowadays. So it's very important to master and to tune these interfaces. So you can do it several ways. So we proposed time ago, we proposed to use 2D material like graphene and related 2D materials. So we started this journey supported by the graphene flagship of the European community. And you see then we did a lot of effort in this way. And then you can see, for example, this is an example, we were using graphene flakes in titania. And on the other side, we use reduced graphene and functionalized molybdenum disulfide, a sort of van der Waals crystal, 2D crystal, at the interface between all transporting layer and the perovskite. So this was the arrangement we did. And the position was very simple. So we were using spray coating technique for the 2D material. So it's still a solution process. And you see with the mapping, very simple, the most simple perovskite you can imagine. So we were able to push up even beyond 20% by tuning these interfaces, the efficiency of the solar cell. This is not limited by the efficiency. This also has a strong impact. The use of 2D materials has also strong impact on the stability of the solar cell. I would like to show something which is not the result of our group, is the results of Michael Gretzel. So this is a sketch of a solar cell where you have gold and copper thiogenate interface, and then the rest of the solar cell is a copper thiogenate all transporting layer. So if you stress this cell under light soaking at 60 degrees, immediately you have a reduction of the efficiency. So this is the efficiency as a function of stressing time, hours. And then you see for conventional solar cell, you have immediate reduction of the efficiency. So you degrade immediately, instantaneously the solar cell. But if you put a reduced graphene oxide, let's say graphene, at the interface between gold and copper thiogenate, you immediately stabilize the efficiency of the solar cell. So you can control even the ion migrations at the interface. Even gold could migrate into the perovskite, and this will degrade. So by putting this network of 2D material, you can stop this kind of degradation. So also for stability, this is very, very important. Recently, we were indeed trying to find a different idea for the use of 2D material that also can impact the perovskite. And we were focusing our attention of mexenes. So mexenes are 2D materials made by few layers of transition metal, carbide nitrides or carbon nitrides. Is, for example, the most famous is titanium 3 carbon 2. This is the kind of material you can change atoms, so you can change also metallic semiconductor characteristics. But very important, I would like to point now, very important is that you have a surface, and you can functionalize the surface typically with oxydrayl group, oxygen, fluorine groups. It depends on the chemistry you do for getting these materials. And so this is very important because you have a very a surface that can be functionalized. And why this is very important, let me show you in a moment, is exactly this. So let's plot the work function, the calculation of the work function made by density functional methods. So this is, for example, is for the bare without functionalization T3 carbonium 2. So the simplest mexene is a work function between 4 and 5. Now, if you put oxygen as a termination on the surface, you move the work function up to 6. If you use fluorine, is between 4 and 5. But if you use the oxydrayl group, you can go down to 2 electron volt. So we have a system, the mexenes, that depending on the functionalization, you can tune the work function from 2 up to 6 electron volt. This, for everyone who is doing devices, is a fantastic wonder material because you can tune indeed the work function. So what we were trying to consider is to use this material to also to change the work function of the material forming the perovskite solar cell, in particular perovskite or the other material. For example, you can see here this UPS measurement. You can shift the work function from 4.72 electron volt without mexene up to 4.37 with perovskite with mexene. So we can tune the work function. So let me make the story short. You can change the band alignment between layers and perovskites. And this was the effect. So this was the efficiency of a conventional solar cell, and then apply the mixins in different points, also guided by simulation, we were able to push the efficiency for a simple perovskite up to more than 20%, and we completely reduced the hysteresis of the cell. So this is a practical technology. We are applying this now in many other devices. There are other publications I would like not to show now here, and also for the stability of the cell. So this was more or less our effort in using 2D material, efficiency as a function of the 2D material we were using, and more or less at the moment we are above 20%. We are not pushing up to the record because it's not simple to get the contest to get the records. But anyway, it's good enough for us because we are focusing mainly on the upscaling. There is an interesting point also pointed out by the Kaneka talk before, is the tandem. So how to go from 20 up to, for example, 20, more than 25, more than 26. So we have proposed a very simple solution for the tandem, is a mechanically sticked tandem. So you take a conventional heterojunction silicon solar cell, you know, the one you can buy from a company. Then you create a perovskite, top perovskite, of course, should be with TCO on both sides. And then you mechanically stake the two. So you push one on the top of the other. So it's a sort of wafer bonding. So we were doing this, and then we were using also 2D materials to improve the efficiency. So this is the top perovskite solar cell. This is the screwed, mechanically staked 2 cell. And this is the final efficiency. So we were able to push the efficiency from 24.2% up to 26.3% by using graphene in the titania. And we got a stabilized efficiency of 25.9%. So this is a very simple way. It's easy to do in this way. Also, the 3-terminal it comes for free, the 3-terminal. So this bonding strategy is a simple way, one of the simplest way to get a tandem, even performing tandem more than 26%. So let me spend the last 5 minutes to show what we are doing to scale up this technology to the module level. And this is some example of module made with 2D materials control of the interfaces. And for example, this was something that presented at the World Mobile Congress almost 3 years ago to recharge mobile phones. This is a module with 1.45 watt. The active area is 110 centimeters square. The efficiency on active area is 13.4%. And we were using 2D material, boosting the efficiency by using 2D material from 11.7% up to 13.4%. So you can do some optimization. You can get 15.3% on a little bit smaller area. And nowadays, for example, we are even using mixins and the best optimization for a larger module, 140 centimeters square active area with an efficiency of 14.7%. So, I mean, is it possible to use this 2D strategy? It's quite compatible with a solution process printable technology. So it's a very effective to get indeed improve efficiency and also stability, but I have no time to show the stability results. So at the very end, this is the progress we did in our laboratory in the years. So we were the first in the world presenting the perovskite module. And then we did effort to improve. And the last one with a surface which is more than 50 centimeters square, but I cannot give too much detail. I mean, we need to still to publish this, is 18.45%, which is, I believe, one of the most efficient module on this size. And this is fully perovskite single junction module. Of course, I mean, module is not enough. And as we know from Japan rules for putting an object in the market, so we need to do a field test. So field test is becoming very important for perovskite technology. And this is our plan, we did actually, to realize panels and then to create a field test and to do this in a semi-automated methods. So we were able to create, to realize not 800, but 400 modules, almost half of them still, and half we need to prepare still. And this was the stuff, modules, small modules. Then we laminated all these modules in a panel. And lamination is a quite tricky problem because, I mean, temperature, lamination, chemistry, and so on and so forth. And sorry for that. And then you see we use a commercial laminator. This is in collaboration with Gretzer Solar. And this is the distribution of the modules. So the modules, there are some spreading in the efficiency of the modules, but we get also even more than 70% efficiency. And this was the test of the module. So we lose, so the average of module efficiency was around 30%. The average of panel efficiency was between 9 and 10. So we lose 2 or a little bit more % efficiency in the lamination. So lamination should improve a bit. And we realized the solar farm in Crete. This is the solar farm we are continuously testing in these days, and we will report, I mean, the results of the solar farm and degradation of the panel made with graphene and perovskite technology. So I can conclude now. And as you can see, I mean, perovskite, but also disolar cell. Disolar cell is a quite rugged technology and can be used in different applications. In agrivoltaics, for example, is very useful in sensors, as Niyasaka-san was reporting. Perovskite is very interesting. I mean, the stability of perovskite indeed was improving in the years, and also 2D material are playing an important role. Tandem is an interesting technology, I mean, and we need to work on the tandem, and there are several ways to do, as Kaneka was showing before. Field tests are now essential, so we need to validate our stress model, accelerate stress model with the field test. I believe is a very interesting point now for Europe and Italy in particular. I would like just to report the announcement made by a week ago by Francesco Starace, which is related to Ambassador, that I mean, Enel is ready to scale up to 3 gigawatt the company for production of solar panel. And as Kaneka was showing, Tandem is in the roadmap of technology platform for photovoltaics. Thanks a lot.
Thank you very much. Thank you very much, Aldo. That was very interesting and amazing progresses you made. So now we are ready for the discussion. So if I can summarize somehow what I've seen and heard, it's that we are having a number of new technologies somehow, I mean, that are competing with the conventional silicon technology for solar cells. So the idea of Kaneka said that still we are going to use crystalline silicon. I would like to start with this this question. So which will be, I mean, those new technologies, the perovskites, the dye sensitizers, which technology is going to prevail in the future? So there will be space for commercial application for these new technologies. And I would like to start with the industrial point of view. So asking first the question to Engineer Imbotti. And I mean, I would like also to listen his impression of these new technologies that he has seen in these talks. Please.
Thank you very much. I think I am not the best person to answer that question because, well, first of all, I would like to thank all the presenters because the professionality, the success of the resist research work which I've seen is impressive. I hope it comes to industry very soon. We will do whatever we can to support such research efforts. I think all what I heard is absolutely in the right direction. Now there's a question of course, in industrialization, which as everybody knows is a very expensive, very complicated job. We are happy to support if we can, both from the office in Tokyo and the office and the people in Italy. We would very much like to be together with you on some of these research efforts if it is useful. And I think Perovskite is amazing material. The work which has been done is amazing. And we are very anxious to see when it will be possible to print such materials because that will revolutionize the industry.
Thank you very much. So I pass the microphone to Professor Miyazaka. So how do you see the possible commercialization of perovskite fuel cells, and that will be the future, and when this will be the future for this technology?
Yes, perovskite is really amazing materials, and it has many advantages, except the problem of use of lead. So the big barrier before industrialization is use of lead. Amount of lead is very small, limited. It corresponds to just 1 centimeter thickness of the natural soil. But if the government allowed us to commercialize, the company is still worrying about any possible risk in the users. If user reject, so they have to say stop manufacture. So this is big. So other problem is the stability, but I believe the stability is now slowly being improved, and it will reach the practical level in short time. Especially for, I think that one of the best application is there in IoT society. So small device to the power, say, Bluetooth wireless device. In Japan, the Rico also already commercialized a solid state dye sensor solar device, and they wanting to replace it with perovskite, but still there is a problem with lead. And but anyway, so electric vehicle application is almost also promising. I think it is the most promising because, say, the lead acid battery we are using in our car, the lifetime is only, say, 3 to 5 years. If we found some loss in energy, say, performance, we go to the dealer's shop and they said, oh, unfortunately, your car battery is degraded, say, 50%. they want to replace? Yes. How much? Let's say $300. Okay, please do. So they can change the battery just after 3-4 years. I also changed my car batteries last year. So same thing can happen for, say, solar cell placed on top of a rooftop. So there is no users, no driver who try to discard the solar cell in some place. So all people are supposed to go to the dealer's shop to replace a solar battery. And also perovskite is very lightweight. The car makers are only accepting lightweight things and cheap things. The perovskite device also cheap and flexible. And we don't have to achieve so long lifetime, 10 years, 20 years for car use. Maybe 10 years is sufficient because we can replace if the device is very cheap, similar to say just paying $400 or $500. And efficiency is high, especially for the weak light. Even in sunny day, car have to run under skyscraper inside building. So there is many shade. There is a very strong light variation, sunlight and shade, sunlight shade. But even in the shade, the perovskite can utilize this weak light to output relatively stable voltage. But silicon, it's not like that. Silicon cannot work under very weak light, especially crystalline silicon. So problem is if we manufacture silicon perovskite tandem cell, so silicon voltage can drop down in weak light. Perovskite voltage may be stable. So there is some matching between the two devices. So anyway, I hope some company try to develop lightweight, cheap perovskite high efficiency flexible device for using car. And if car company make an infrastructure to sell, well, mount device on the car and start safe recovery, 100% recovery of device. So this industry can run. So this is my, yeah.
Thank you very much. Very interesting idea. So Alberto, just going to the stability problem of perovskites, we were very skeptical some year ago that perovskite would make a market because of the problems of chemical stability and I mean and reactivity with water and this kind of problems. Are you still skeptical, or did you change your mind?
But for say thermal stability, the perovskite will not compete with silicon because they are ceramic, gallium arsenide and CIGS are ceramic. They're stable up to say 300 degrees C or something. So as long as we are using the organic cation for high efficiency solar cell, so thermal stability limited less than 200 degrees Celsius. So now we are trying to make the all inorganic perovskite that will work at high temperature.
Yes, that's very interesting.
Yes, thank you, Enrico, for the question. I guess that now there is hype towards perovskites because, of course, they reached an impressive photo conversion efficiency. And if you get, of course, full inorganic photoactive materials, it might be that you are able to solve the issue of stability. I guess that the option is not really only about stability, but it's also about what kind of application you are targeting. Because in specific applications, you may reduce your constraint about stability. For instance, I was presenting something about building integrated photovoltaics. In some facades, the glasses cannot be changed. It's extremely costly. But in our applications, like for instance, parts of roofs or parts of architectural parts that can be easily removed, stability might not be a severe issue. And in addition, it also depends on what efficiency you expect, because for instance, for some domotic applications, efficiency is not so critical because you don't need a power density which is too high. You just need a power density to lower the impact in the grid. And you may use your building like an off-grid self-sustaining device, I would say. And in this respect, the issue of stability may be reduced. I'm still not fully convinced about the success of perovskite, but I'm not working in the field, so I would invest in luminescent concentrators because I like this application. But
yeah, I agree with you for especially the application of Windows. So
yeah.
if the perovskite, say solar cell is lightweight and like a kind of film type, we can put the solar cell inside of Windows, not outside.
Yeah.
So inside the window exposed to the room air, the air-conditioned room. So no solar cell is exposed to high temperature, like 60, 70 degrees.
Yeah.
And you know, there's no rain inside.
Yeah.
And this application, and we can also attach the module to already built Windows. So we don't have to replace Windows. So the construction fees are very cheap. This is a good way to application. Yeah.
Would I now to ask the opinion of Aldo, who's instead, I mean, is trying to solve this problem with practical issues. So how do you see this issue?
So thanks, Enrico, thanks a lot. I would like just to discuss 2 points. I mean, that was this previous discussed by the other speakers. So one is the lead and the other the stability. So for the lead, I completely agree. This is one of the psychological, I would like to say, barrier for the perovskite. I want to say psychological because if you do, and as many studies now are doing, this life cycle assessment for perovskite technology, the life cycle assessment, the footprint on health and environment of perovskite is much less than a conventional silicon source cell, but at least 2 orders of magnitude. This is very interesting. The point is that we are mainly based on ROHS directives. So it's a chemical-based directive for health. And then if you have a material inside, I mean, you cannot make the device, or there are a lot of problems. But as I said, LCA show some different stuff. So I believe at the very end will be a regulatory problem. So we need to move to certification which are based on life cycle assessment. Like eco-design and other certification, which are really based not on ROHS, but on LCA. I believe Europe is moving in this direction. So you need to see all the story of a device, of a system, to get it compatible with environment and human life. Of course, I mean, nevertheless, we need, as photovoltaic industry by per se, we need to provide a roadmap for lead reduction. So I believe, as Miyasaka-san was saying, I mean, we can move to other materials, like we can reduce lead with tin, germanium, so other materials. We can make the solar cell thinner and thinner, so the content of lead will be reduced by using light management, for example, technologies. So this is for what concerns lead. The stability, I've seen that progress are really enormous. And nowadays, I believe we have more than the record is more than 200 hours under light soaking, 2,000, sorry. More than 2,000 hours under light soaking without degradation. Encapsulation is good. perovskite is becoming more stable. So we are learning that, I mean, defects are ruling some stability. So I believe we are learning a lot of stuff, and the effort has been enormous, and the community is very large of scientists around, and they are promising. And also I want to say there's combinatorial methods based also on machine learning, artificial intelligence is also driving this revolution, finding new combination that could be stabilized more and more. So I believe stabilization will be achieved, I believe, quite soon. And the point is the market at the very end. So the market is quite critical because, I mean, is enough to have a panel with 22% efficiency if we have silicon where is already scaled and so on and so forth, as from you have economical scale of the panel. So this is, I believe, is still an open issue for. I think that the tandem could be one of the first solution because you can feed the development with also silicon provider. So because they are interested to do the tandem. So probably tandem could be one of the first application. Of course, with perovskite, you can do perovskite tandem. So maybe you can have a perovskite module, very efficient perovskite module, but made not with a single junction, but with a multi-junction, perovskite multi-junction. I believe this could be a way to enter in the market. Low light is also very, very interesting because I believe between disolar cell and perovskite, there's a strong competition for low light. And then every month we see one of the two technology pushing the record more and more. So low light so IoT is very interesting. Of course, there is, and the last, and then I'll finish. You can print conformably. So printing technology could help. But I mean, we know the story of OLED. They can be printed, but industry prefer vacuum technologies to make OLED also on large area. So also printing should, the printing technology, which is really interesting because, you know, you can scale up, you can make comfortable, flexible, and so on and so forth, should solve some issue, for example, to be green. So the solvent you are using should be green. So I believe we need to put also research effort on getting a green chemistry for perovskite.
Carlos says, Carlos-san, I have one general question. The tandem making is a very hot topic now. And my question is, the perovskite solar cell can reach efficiency kind of 26, 27% in future. If tandem reached beyond 30%, what about cost performance comparison between single perovskite able to say have 27%? On the other hand, tandem with 30 to 30. So how much more expensive cost we can invest to buy the tandem cell? Because the difference is only 5%. So same question I like to ask the Kaneka-san. This is always I'm saying, my dream is to mimic the gallium arsenide, the 28% by perovskite, by say increasing not decreasing band gap to 1.5 or something, and making very small say voltage loss, so we can achieve in future 27.8% with single cell. It's the cheapest example. But on the other hand, tandem is automatically cost is higher. So this is my question. Yeah.
I'm not a specific answer on the cost. I know the target. The target is made on levelized cost of energy. So the levelized cost of energy should go down to below $20 per megawatt hours. So if we reach this with the tandem, then is a commercial technology to me. If we don't reach this with the tandem, then it will not be a commercial technology. So we need to go, should be very aggressive, it should be well below 20. Of course, this will depend on many where you are. So, but I mean, the best condition, I want to say, should go down to this.
I heard several years ago, the Oxford PV UK, they suggested that they were trying to move from perovskite silicon tandem to perovskite tandem. Why? The answer is it's cheaper. Okay. And the perovskite tandem has a same thermal expansion index. So junction of ceramic silicon perovskite half organic is also some issue.
Miyazaki-san, thanks a lot, I mean, for this issue, because I mean, we cannot believe, but as you said, one of the most critical problem, even for the solar cell, is the mechanical stability. So mechanical stability, we never tackle, there is no publication, I mean, very few, but I believe is the most important problem to solve. It was the most important problem to solve for the solar cell. And I believe, as you said, because you have strain, a lot of strain, different thermal expansion will be one of the most important problems to solve, even for perovskite, especially when you go for.
Yeah, I have been always impressed by the DSSC, they developed by your company. It's beautiful, excellent. And now the DSSC can be immediately commercialized because without the use of lead, it's immediately acceptable. Yeah. So if say Rico developed the solid state DSSC, what about your DSSC module? It's a solid state or liquid junction? I hope it will be converted to solid state. Okay, anyway.
I don't know if Dr. Mishima wants to answer to the observation of Professor Miyazaki.
Yeah, so now it's difficult to say about that, but of course, it depends on module structure and the volume. So considering current situation, so the price of crystalline silicon substrate is going down and lower and lower. And on the other hand, the volume of the thin film solar panel is not so high. In that case, glass TCO. So normally, when people make thin film module, so they need to use glass TCO substrate. And that price is so higher. But of course, if 26% single junction perovskite is realized, and so people want to get so the volume is bigger. So I don't know. So what will happen? So let's see future.
Thank you very much. So we are running out of time, but I want to ask a very quick question to Aldo. Very quick answer. There is still space for dye-sensitized solar cells in the future.
I mean, the potential for the solar cell is very high. I mean, if we know where we lose voltage, and then we can, and also fill factor, unfortunately, so we can really push the efficiency of the solar cell to a higher level. So I believe it's very interesting problem for the scientific community. So the potentiality is there. We need only to understand a few things. And I want to say that this happened, for example, in organic photovoltaics. Organic photovoltaics was surviving not so well, but then the people understood that there was a problem with the C60, and we're replacing C60 with acceptor that are not fuller and free acceptor. And now, you know, organic photovoltaics based on polymers can reach 18%. It was really a breakthrough in the science. I believe the same breakthrough should be for the dye solar cell. And then, as Miyazaki-san said, I mean, you have not lead, you have tunability, you have a lot of potentiality for dye solar cell. You can do even on solid state. So I believe, yes, but we need to do some effort. And nowadays, I mean, all the people unfortunately are focused on perovskite and left solar cells. So maybe in few years we need to reconsider completely this activity. Yes.
Okay, thank you very much. I thank again, now we're running out of time. I'm sorry if I could not give all the answers, but I thank very much the speakers for the very nice talks, nice presentations, and very, very lively discussion. So thank you very much again, and have a good day in Italy, and have a good night in Japan. Bye-bye.
Thanks a lot.
Ciao.
Bye-bye.
Of time, I'm sorry if I could not give all the answers, but I thank very much the speakers for the very nice talks, nice presentations, and very, very lively discussion. So thank you very much again, and have a good day in Italy, and have a good night in Japan. Bye-bye.
Thanks a lot.
Ciao.
Bye-bye.
Ciao.